basically. This is the chapter 4, the unsteady heat conduction or transient heat conduction. So we are tracking the problem when we just put the rod on the candle, or we just start boiling the water. What happened to the temperature of the water? How long does it take for the water to boil? How long does it take for this to hurt your finger? Right? Like how long you can hold it before it to say ouch, and you just basically drop it from your hand. So why this problem is hard? Because you have to now deal with the whole equation. You cannot neglect the unsteady term anymore. Now, so let's neglect the E dot generation so that we don't make our life miserable. So if we keep those two terms, the conduction term and the unsteady term, this is very tough mathematically. Because why it's very tough mathematically? Because it's partial differential equation, because t is function of x and t is function of t. So the temperature, the solution integrating this should give you that t is sine x multiplied by e to power at, where a is constant, but it's function of t and x. And if you remember, one way to do this is to take it to do Laplace transformation, turn it into the S domain, get the solution over there, and do inverse Laplace, bring it back again to the... And so the physics, so the math of partial differential equation was not fun. I mean, that was not really my favorite math course when I was undergrad. Solving partial differential equation by Laplace transformation. So we need to simplify the problem. So one way we'll try to simplify the problem is, let's not make it partial differential equation. Let's try to make it back into ordinary differential equation. All right? So you guys have to tell me how we can do this. And then the second part would be, well, we cannot simplify it. Let's just solve it as it is. And since the solution will be really hard, we will actually get the solution in tables. So we don't I will not ask you to do partial differential equation. Let's keep this for grad school. All right? So for now, let's first find a trick to turn this into ordinary differential equation, or basically make one of those variables disappear, the x and the t. One of them need to disappear. Which one do you think can disappear?
dt dx.
You can get the x out of the, how you're going to get the x out, or basically make it not relevant or not important.
Or take the time out and just do it at certain times.
Well, then we already did this. That's what we did in chapter 3. We were basically, you could think about chapter 3 when we were doing the steady state. It was as if, so Mallory was saying, why don't you just do it for the first second where everything was almost constant, and then do it again after the next second and the third second. So during every one of those seconds, the problem would be as if it's steady state. That procedure is called quasi-steady state, where you solve the problem every time step, kind of. But this, we already did this kind of when we actually did chapter 3. No, I would like another way to actually get rid of one of those variables, x and time. Huh?
You can get rid of the x domain by treating the whole mass as the same temperature.
Excellent.
So you're not looking at the temperature at each individual component, just the whole thing is one temperature.
Excellent. Excellent. What's your name again? I forgot. I'm sorry.
Devin?
Devin is saying, why don't we treat the whole thing as just one x? There is no temperature distribution inside. It's not like this water, one part is hotter than the other. The whole water is sitting, it boiled together, it cooled together.
Does K have to be high to do that?
Wow, excellent. What was your name again?
Jason.
Jason is saying, well, he said if you want to do this, you have to make sure that the K is really long enough, K is big enough, so that you can really manage to do this, so that you can basically say they are all at the same temperature. And as my discussion with James earlier today about this fan, it will never just be the K. It will have to be a ratio between two things. One of them trying to bring the whole thing as just one Lambeth mass. That's what we call this approximation. Lambeth mass analysis. We'll bring the whole thing into one body at one temperature. And between the other thing that's preventing us from doing this, the other thing that's saying, No. The middle of the water is different from the edge of the water is different from, right? But you guys are doing a great job. So let's see what can really make us do this Lambeth system analysis. The whole piece of meat is at one temperature. Imagine you have a piece of meat and you're trying to cool it in your freezer. Will it cool as one piece? All the edge will basically get frostbite while the middle, or actually let's cook in the grill instead. So if you are cooking on the grill, you know, will you end up charring the outside while the metal is still bloody?
Yes.
Or will the whole thing really cook together at one temperature? So what determined this? So Jason's saying K, right? And it's actually, it must have, K is the conduction, but also it must have, how is this thing is being heated or cooled? It's because of, why this piece of meat is being heated on the grill? Convection on the outside, right? So it's a competition between how quickly the convection is heating the edges or cooling the edges in case we're freezing it, and how quickly does the K manage to bring that new temperature on the edge in the center line very quickly. All right? So we just need one length scale so that we can make it dimensionless, because K is watt per meter Kelvin and H is watt per meter square Kelvin. So some students actually get confused about the K. Is it the K of the meat or the K of the air, the hot air around the meat in the grill? Which K we are talking about? The K of the meat or the K of the hot air around it that's trying to heating it? The K of the meat. And it's the H of the hot air, right? So later on in the course, we will have K of the air, not K of the meat. That make it completely different number. So remember that it's, so now we are, of course, we're talking about the K of the solid and H of the fluid around it, right? So Q here on the outside is happening because of that convection. H area T infinity minus T inside, right? This is if you manage to make that dream that the whole thing is just sitting at one temperature. And if we actually can say that this approximation works, we track the equation that track this guy is pretty easy. It's basically simply the Q coming here will increase the internal energy in here. It's really the first law of thermodynamics on a system. Q minus W equal delta U, right? Of course, there is no work involved. So Q equal delta U. You give me certain joules by convection, I will just take my temperature up. My internal energy, MCB delta T, will just go up, right? All one temperature. So let's find out this magic number. Well, let's go to this magic number first and then I'll show you the solution. So this magic number is H multiplied by a length scale over K. That make it dimensionless, right? And that magic number is called the Pike number. Alright? And so now, if this Pike number is really small, smaller than 0.1, so it's not 1, it's not like they have the same order of magnitude, but basically the H is really tiny compared to the K, or the H times scale is very tiny compared to the K times scale, then the Pike number is tiny, and therefore that Lambeth analysis work. We can just think this piece of meat is one piece. What if K is 1? Well, no, they are not. The K is not really winning. Alright? So for K to win that competition and make the whole thing sitting at one temperature, Pike number need to be less than 0.1. Alright? 0.01 even better. Right? And so what is that length scale? Again, it has to do with it's really the H, the area playing with the H and the area playing with the K. So it's the volume over the surface area. So you can imagine the volume is basically what the conduction is trying to act on, and the surface area is basically where the heat transfer is happening. Alright? So you get the length scale by dividing the volume of the piece of meat or the volume of the tomato that we are going to solve today or the baby milk bottle. So that would be the volume divided by the surface of that baby bottle. All right? And so if that length scale multiplied by h divided by k is less than 0.1, then you would say, well, I think that milk will warm up, is basically as if it's one temperature. All right?
So we could essentially take something, we could basically change its shape to give it a different characteristic length and actually help the process along.
That's excellent, especially if you are trying to make the h lose the battle and increasing the k. So you basically make sure that the h doesn't have that much area to act on. So you basically pull all your meat into one big cylinder so that you reduce its area, and therefore the k will have time to actually heat the metal. Very good. All right. So some of the problem last year in the exam was basically just to ask them, can this problem be treated as Lambeth mass analysis or not? Not actually to get the solution, just to check, can we treat it like this? And so all they have to do is just to check the byte number, all right? Or calculate the specific or characteristic length by dividing V over the area and basically say HL over K, how much is that? All right? So of course, if this is the baby milk bottle and you would like to warm it up, well, guess what? If you actually calculate the byte number, what do you think will happen? Actually, it's a problem in our textbook. But what do you think the solution would be? Will the byte number be small and this problem can be treated as Lambeth analysis, or no, the byte number will be really big and it cannot be Lambeth analysis? What's your guess? No, it's not. And so that's why if you have a baby, you know that you have to
Oh, sorry, you have to stir it.
while you are steering it, while you are trying to warm it by hot water, because you realize that, well, it's not at the same temperature. So if you steer it, then that's another thing that to actually try to make the temperature uniform in the middle, right? So then, but of course in solid you don't have this option. If you are cooking the piece of meat, you cannot really take part of it and mix it while you are heating it. Right. So we said this would be the equation then, and so integrating this equation to get the temperature as function of time, that is the solution. The temperature is not function of x anymore. Temperature is only function of time. It will start from T initial, and eventually it will go to. Eventually it will go to what? We start from T initial, and eventually we will go to T infinity, the air around you. If you give it long enough time, of course it will get the air temperature around it, or the fluid around it, right? Right? Long enough, it will reach that temperature. So he's integrating now. So HA T infinity minus T time delta time MCB dt. Where did this come from? He just see, this actually was, the Q was HA delta T, and here it was MCB dt by d time, or the rate of change of the internal energy. So what happened is he basically make it dt here, and the t time that was in the denominator he bring it over here. All right. So he will change the variables. So basically, rather than saying it's dt, we can make it dt minus t infinity. So for example, if I'm integrating tx, it's the same as dx minus 5. Because the constant, when you differentiate the constant, you get 0, nothing. All right? So this equation can be written as, or this temperature can be written as dt minus t infinity. Why he's doing this? So that now when he bring this in here, it become dt over dt minus t infinity over tt minus over t minus t infinity. Alright? So this is like dx over x. And we all remember the integration of 1 over x is ln x. Right? And the rest can go to the other side. So the rest is MCB and H area, and that mass is basically rho time specific volume. Sorry, rho time the volume, density time the volume. That's the mass. So basically, it becomes HA over rho VCP, and this is all constant. It's not function of time. So when we integrate this and we get ln, this guy basically become just the constant multiplied by what's the indication of dt? T. Okay? Correct? So if you have ln x equal t, that means that x is e to power t. So if ln the temperature is this much, then the temperature is this guy to power e. So e to power minus all this time t. Or basically, if we call all this, this is all this, HA rho VCP, it's P. So we can just make it short by saying that t is equal to e minus pt. So if you plot this, it will look like this. It makes sense because when you put t equals 0, that's the initial time. E to power 0 is 1, and so t is at t equals 0, this is 1, and therefore the temperature is, no, the temperature is, it's not t infinity, it's t, ti, exactly, it's ti. When t equals 0, this is go to 1, and therefore this go to this, or t become ti. So they all start from ti.
What is the B?
So it's all this. See, the B is HA over rho VCP. They just didn't want to say it's e to minus HA over rho VCP, so they decided to make it e to minus PT, just to make the solution shorter. But it's, remember, ln x is equal t, then x is e to power t. So that's ln x, and this is the t. This is the stuff in here. So you just raise it to that power. All right, now the other extreme, when t go to infinity, e to power minus infinity is 1 over e infinity. It's 1 over infinity. It is 0. So at t equal infinity, at very, very long time, this guy would be 0, and therefore t is, so all of them eventually are going to t infinity. All right, and so how quickly do they rise? It really depends on the b. So if b is really big, it helps the time. So with a really big b, the time will move very quickly. So if you have a b that's 10 times bigger, the time, you don't have to go to 10 seconds. At 1 second, it will be as if it's 10 seconds for another material with a lower b. What is the b? H. Again, look at this. It's always a competition between what's trying to make the thing get hotter and what's trying to make the things sluggish and doesn't want to get heated up. Right? We are tracking how quickly does it go to t infinity. This is already assuming k is really big and the whole thing is acting as one mass. Yes, it's acting as one mass, all right, at the same temperature, but still it will not get heated up that quickly. You still take 1 hour to cook the chicken. 45 minutes. Oh my God. So why does it take 45 minutes? HA over rho VCP. So if rho VCP is really big, that is the storage. It's the mass times the CB. It's the joule per kilogram multiplied by kilogram. So if the kilogram is really big, or the CB is really big, this thing, you keep throwing joules on it, and the temperature doesn't want to go up. Because there is just a lot of place where he can, or a lot of storage where he can dump the joules in, and the temperature will not show up. Of course, what's competing on the other side, H time area. Yes, you have this much mass, but I am turning the whole thing at full power. So I'm going to heat this turbine or this boiler very quickly, because even with the very high heat capacity of the water inside the boiler, I'm putting a lot of HA. I'm turning a lot of flux on them. Right? So basically, as B get bigger, the T much quicker, or basically that curve jump like this. Okay, he go from Ti and it just jump to T infinity. And as B get really small, he will take forever to reach that temperature. Okay. So now let's solve one problem. So let's solve this one. So this is problem 25 in our textbook. And he said steel rods are quenched in a hardening process. Sometimes they would like to get very hot steel and just drop it in the water so that the surface treatment is working. And so the average temperature of the rod when they are taken out of the oven is to be determined. So he actually would like to get the temperature after 40 seconds. Require the temperature after 40 seconds. So initially it was 850, and he dumping it at 50 degrees C water, and he give you the rho, the CB, the K, H, and L, and D. Alright? So in this chapter there are ways to treat this rod as basically a cylinder with different temperature distribution, and we are going to go through this. But I mean, obviously, since we only had the Lambeth mass analysis so far, this problem is probably going to be solved using Lambeth mass analysis, right? But however, in the exam, you have to justify, should I go this easy route or should I go the really long route that we are going to see after the break today? So what can justify us taking the easy route? The byte number. We have to check it, right? So to be able to assume Lambeth analysis, I will have to basically get the LC, the specific volume, sorry, the characteristic length, by dividing V over area S. And so the V would be, what is the volume of a cylinder? Anyone?
Pi squared, yeah.
Pi over 4 D square multiplied by the length. So D is this guy, and of course L is the length of the cylinder. That's the volume, and the surface area would be by DL, right? The circumference times the length. And one of you should jump on me and say what happened to the right, the two ends. But see, it's a 2 meter rod and 4 centimeter diameter. So yes, of course, if you want to be accurate, go for the 2 caps. Right, but probably it's not going to change the number that much. But yes, if you want to do it accurately, do it this way. So this will end up being D over 4 for a very long rod, or basically 0.01 meter. And then we can check the byte number. It's H LC over K. So we have the H, it's the 650. We have the K, that's the 63. And we got the LC, and this become 0.102. So 0.1, and therefore, you know, it's close to 1. So he said smaller than or equal 0.1. So it basically that the K time scale is much, the K is much quicker than the H, right? It's not, they are not the same order of magnitude. The K is winning. It's 10 times faster than the H. So basically you would say then, well, we can use Lambeth system. Alright, so we can use Lambeth system. Okay, so there was only one equation that we saw, the T minus T over T minus T equal to E to minus PT, remember? That is the equation describing or that curve that we have seen, where things are rising from Ti going all the way to T infinity as function of time. that was the equation that you will use. So it's t as function of any time minus t infinity over ti minus t infinity is e to minus bt, where t infinity is the 50 and ti. So actually, notice one thing, that in this problem he's being cooled to t infinity, right? So actually, if I would like to draw this accurately, it will really look like this. It will come from ti and it's slowing down to t infinity, correct? So from the 850 all the way to the 50, and he would like to find after a few seconds, 40 seconds basically, what will happen. So all I have to do is just substitute for the b and get it, and get this equation running for us. So the b was the surface area H divided by rho V CB. Again, the heat transfer from the outside, the storage inside. So S H over rho V CP. So you plug all those numbers. You have the H, you have the area, you have the volume, you have the CB. If you don't have the CB, you just get it from the table for this particular material, but I think we were given the CB. So the CB for the steel was 434 joule per kilogram Kelvin, and so this become 0.019. What do you think the unit of the P is? Can anyone tell me what's the unit?
1 over seconds.
Excellent. 1 over second. Jason, right? So because it's e to power minus bt, so b and t must have the opposite units so that they cancel out. All right, so you guys can just, now you know the ti, t infinity, and the t is 40 seconds. The t will end up being 422. So he dropped from 850 to 422 in just 40 seconds, right? That's how quickly the H is. Question about this? So again, to use this simple solution for the temperature, you just have to check first the byte number. If it's 0.1 or less, you are okay. If it's not, like the milk bottle problem, actually in the homework problem, he said the bottle was continuously being stirred. So even if you check the byte number and you realize that, well, it's not 0.1, it was like 2 or something, but he said in the problem he's continuously stirring it, then you would say, well, I guess the fluid inside will keep the temperature constant throughout or uniform. So I can actually use that because of this as treatment of the fluid.
Could you also assume, like, say there's a sandwich, they're grilling a burger or something, they flip it every.
That's another way. So if the problem is hinting that he's basically trying to keep the temperature the same, then you actually go the easy route, because the other route is not really fun at all. We'll see it now. Actually, even understanding the table that we will use is not easy. So, but we will have to solve problem also the other way. Okay, so again, here is the criteria that we have to check, and we will see actually why this magic number was actually chosen to, right? But let's take our 15 minutes break now.